Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Dear students, today we go to the next chapter, which is about the syntax analysis. The syntax analysis is something which is done by the parser. Okay, we are done with the lexical analyzer, where we saw the source program got converted into tokens, and we got lex. We saw the lex, and there's a lot of things here, and it used the automata, and the parser uses the yak here, the equivalent of the lex. They work in the tandem. Tokens. Parser asks for the tokens. When it gets the enough tokens, it will start converting a parse tree. Actually, it try to see the syntax. It does the syntax analysis and try to see whether it is syntactically wrong or right. Okay, is it valid or is it wrong? Okay, which can't be done by the lexical analyzer here. Okay, so what we got is the program, some sort of program, and we give to the lexical analyzer, which we did saw in the previous videos, that we see the token stream built from the by the lexical analyzer, and these tokens are taken now by the parser, and the parser uses some sort of grammar. The grammar will be the context-free grammar, and we will talk in detail those things, and it will build actually a parse tree if it is a valid token stream. If it is not, we will say there's a syntax error. Okay, now if you look at the goals of parsing, we try to see whether whatever the tokens we have, are they grammatically correct or not. So because every programming language has some syntactic rules, and the tokens have to be according to those rules, and we have the context-free grammar, which we talk in detail later on, and we got to decide if the program satisfies syntactic structure. Okay, and there may be some syntactic errors. We're going to detect them, we're going to recover them, and we have also simplification rules on tokens, and what we build is an abstract syntax tree. What simplification means is we'll talk it. For example, if the token comes up which says like A plus B, or even there is something like this, or there may be something like this, or maybe many times, I don't know how many times it would be, but it is actually A plus B, so this thing is same to this. So we can simplify this here by the syntax analyzer. Okay, so this is the simplification done by the, so extra syntax will be removed by the by the parser, right? Parsing, which you may have done in your primary classes in the English grammar, right? The parsing is same kind, here also. It recognizes whether a sentence or a program, in our case, is grammatically well formed, and actually identifies the function of each component. For example, if I see a sentence which says, I gave him a book. Now if you look at this, we got a sentence, and sentence has many parts. Firstly, the subject. In case here we got the I as a subject, then we got a verb, that is our gave, then we got the object, that is the him, then we got the indirect object, then we got the noun phrase here, and in noun phrase we got actually two things. One is the article, the, and we got the noun, that is the book. Now if you look at this structure, this is the syntax tree, or in our case the parse tree, right? This is which our parser actually builds. So what is the input here? In our case, the input is the token stream of tokens, right? It doesn't take a one token and starts parsing it. Parser takes many tokens, and when it is done with taking many tokens, it outputs the abstract syntax tree. Okay, Now you may wonder why we have separate lexical analyzer and parser. Okay, yes, lexical analyzer uses regular expressions, but the question is, can a regular expression, um, we use it to see the syntax of the syntax, can analyze the syntax or not? But that's not possible by the regular expression. Okay, because there are many languages which are not regular. For example, there is a parenthesis. Now, if we got a couple of parentheses here, single parent, so it's imbalanced. So we have to check the balancing. These parentheses are balanced or not. Now, this thing can't be done by a regular expression. Okay, there is no regular expression for this language. Okay. So because a finite automata, which we talked about in lexical analyzer, may repeat states. Okay, but it can't remember the number of particular states. So we can't just remember that how many states we have, so that it comes back or forth. Okay, because if we have a couple of parentheses here, then it should have a couple of closing parentheses as well. So we can't count how many states we were in the beginning, so that we can match up the exact next cases, because simply we can't count in our lexical analyzer or using the finite automata. Okay, or a regular expression. So we need some kind of powerful language. Okay, so more powerful language is needed, which will describe the valid string of tokens. So simple thing is that programming languages are actually not regular, so they can't be described with regular expressions. As we said, the balance appearances, which is a simple example of a non-regular language. So we use what's called the context-free grammar here, which is push-down automata. We talk about that in depth later on. So we are actually separating the lexical analyzer from the parser. It's better to have tokens, which is done by a very simple DFA, and in a much efficient manner the tokens are formed, and then from the tokens we see whether the tokens are well formed, are they syntactically correct, are they according to our grammar or not, right? Done with the parser. Now a parser can see the syntax is grammatically correct or not, but it can't do many things. For example, whether the variables are of types on which operations are allowed. For example, we are saying what is happening here? Yeah, here. For example, if we say we've got an int x, and I'm putting this is an integer variable, I am putting a character a into it, or I am putting into it a boolean true. Now syntactically this is correct, there is no problem in syntax. You're assigning something to a variable, your parser will take it, no problem, but the semantics is wrong, and that's this thing. It doesn't check the type agreement. Okay, now there may be also, this is the one thing. The second thing which the parser will not do is the variable declaration. For example, you are saying int x here, and then later on you are trying to put this x into something. Maybe you are putting into some variable y equals to x. Now is this y declared or not? This will not be done by the syntax analyzer or parser, because it talks about syntax, it doesn't worry about semantics, because y is not declared, so y can't be assigned the x. So parser has nothing to do with that, it just sees the syntax. Is syntax correct? Yeah, syntax correct. It doesn't worry about the variable initialization or the variable variable declaration. And also the third thing is variable initialization. For example, in this case, even though we have y declared, for example here y is declared as an integer variable, now you're putting in the y x, the x is not initialized, so you are putting actually nothing, which is actually it's a null. So semantically this is wrong because you have not initialized anything to the x, but syntax wise it's correct. Okay, so these things, the three things I told you, the one is the type agreement, one is the variable declaration and variable initialization. They are deferred until semantic analysis, so this is not the job of the parser. Now parser actually are three general types of parsers, but we have usually two types, because the first one is a universal parsing method, second is top down, and the third one is bottom up. But this guy, the universal parsing method, which uses the CYK algorithm or Early's algorithm, they can actually parse any grammars, but they are very inefficient to use in production compilers, so we're not going to use that at all. Okay, so there are basically, so we say generally speaking there are two types of parsers. One is a top-down method and another is a bottom-up method. Okay, top-down basically starts building the tree from the roots to the leaves. So root is on the top to the bottom, right? So it starts building your if you look at this here, the abstract tree, it starts building from the root and starts going down up to the leaves. But the bottom up is which we actually we will take these in more detail. So bottom up will start from the leaves and go building your root. So this is the bottom up versus the top down. Now a parser or the compiler will also assist programmer in identifying and detecting and correcting errors, right? So the errors come in a lot of variety. One is the lexical error. We may have the syntactic error, which will be interested here, and we may have also the semantic error, and then there is a logical error. These two guys will be done on the runtime, and these guys will be done on the compile time. So this is what parser will work on. The lexical errors are simply include for the misspelling of identifiers, keywords, or operators, the typos. Okay, for example, you have to write the int, or you are writing something else. Okay, you have to write char, you are saying chr. So these are the lexical errors. Say for example you have declared a variable called var. Now you want to initialize vr, so this is the lexical error. Now syntactic error is where you have done some lapse in the syntax of a programming language. Say for example you have an opening brace and you forgot the closing brace. Okay, you have a case statement, for example, but you don't have an enclosing switch, so you should have a switch before you do the cases, right? So if you're not having a switch and you're using a case, you are having a lapse on a syntax. You understand? And semantic errors are something like we said type mismatches, like we say int x and we try to put in the boolean. Now this will be taken up at the runtime, right? And logical error is something which logically is incorrect. You can come up with an example yourself. That's not a big deal. For example, you are trying to say x equals to y. Now the intention was to check whether x is equal to a comparison or not, but you did x equals to y, but your intention was the comparison. But so this is something which is the error in the logic, which are tough to take on because we don't know the intention of the programmer as a compiler. So they will only generate wrong programs, wrong outputs. So by that we can understand we have some logical errors, but we can't do much about those things. And semantics will be taken up at the runtime, and syntax error and syntactic errors or lexical errors are dealt at the compile time. Now the precision of parsing method allows syntactic errors to be detected very efficiently. Okay, we have many parsing methods. For example, we have the LL, we have the LR. We will talk about these in detail later. Okay, so they detect error as soon as possible. When the stream of token has come up, it actually. The goals of error handler we have are report the presence of errors clearly and accurately. Number second, recover from each error quickly enough to detect subsequent errors, and also we need to have the minimal overhead to the processing of the correct program. Okay, so we don't want to slow down the processing of any correct program. All right. Actually, we are not in a position to discuss error handling in entirety, but for that we need to understand the parser inside out. But still, we try our hands on it. We know a good compiler should assist in identifying and locating errors for sure, and how it actually a parser allows early detection of syntax errors by a property, what's called as a viable prefix property. What is this viable prefix property is that we have a goal that we want to detect errors as soon as possible without further consuming no unnecessary inputs or tokens. How we do that? Because we know we have a grammar, basically we have a language firstly, right? And we know we have the strings in that language. Okay, we detect an error as soon as the prefix of input does not match a prefix of any such strings which belongs to this language. Okay, that means whenever I see something, say for example I got some while statement or for loop, and I know what lies inside, and I have a set of strings which actually which can be we say that whether this is correct token or not by I just told you that it is by the grammar. We have a grammar. We will understand this properly later on. We have a grammar, but by that grammar we understand whether a particular set of tokens is a valid kind of syntax or not. That means, in other words, is that something a string which belongs to the language or not, right? The moment we saw any prefix of a particular string not matching to these strings which belong to the language or which are defined by a grammar, then we detect the error that or there only, right? So this helps us to detect an error as soon as possible. So how should syntax error be handled? First thing is simply that report errors, terminate compilation, but that's not going to be user friendly because there may be a lot of errors, as we know, in our program languages, so it will halt and halt and halt. So what I do is report error, recover from the error, and search for more errors. That seems to be better choice right now. So good compiler should be able to detect as many errors as possible in various ways and also recover from them. That is, even in the presence of errors, the compiler should scan the program and try to compile all of it. That's what we call as an error recovery. So you're not only detecting, but you are recovering. So if you are not able to proceed further because there are some errors, so you may actually try to correct also that kind of error, right? So our compilers are sometimes very intelligent. They try to recover by themselves, even though that's not a perfect thing, because we don't know, the compiler doesn't know the intention of a programmer, but still there are many ways that we can correct automatically the errors and try to see further errors in a program. So it depends on a compiler. There are some simple compilers which simply detect your error and simply halt it, give a message. Then there are some which actually rapier, okay, and there are even more sophisticated compilers which actually correct the erroneous input. Actually they guess what the user has intended. However, we can say that there are no such compiler, which can be perfect in such a manner, because true correction is very tough to do, because what's the intention of the programmer? A compiler can guess, but there are some limits, right? Because if you want to do the correction in a proper manner, it's only the programmer who can do it. But as a compiler guesses it if it is a very intelligent compiler, right? So we can make our compilers very intelligent. How? because if we have, say for example, some syntax, because this is a for loop and we know there are something here, okay, and if these colons are missing, but we know in our language this is quite simple to correct, because if we miss this colon or this colon, we can just plug it in. Or sometimes there is a comma which is missing or something. Say we have a well-known cases of, say for example, switch case, and we know there's appearances and it should be matching. If this is missing, we can simply plug it in to correct it, right? Because we actually know the syntax in advance. We have a language which we have a grammar which specifies these things. So if it is missing, we can fix it. And the compilers which actually does all the three things are given a special name as diagnostic compilers. So we have diagnostic compilers. These diagnostic compilers actually are much advanced compilers which actually not only detect or repair or even try to correct it. For example, we have compilers like what? For example, we have what for. We have IT Fort. Okay, they are the diagnostic compilers. One of the most famous one is actually the PLC programming language, and then C is for correction. This PLC compiler actually does what? It tries to correct and produce a valid program. Okay, it does it of its own, and it wonderfully does it. You give it erroneous program, it will correct it and always try to make a valid program. And it's very rare that it gives some error message as well. If it can't handle a few things, then it gives you the error message, but maximum times it gives you the correct program. So it is the diagnostic compiler just talking about. So these diagnostic compilers not only does the job of error recovery from the compiler point of view, but also from the programmer's point of view. So it will be really ease. It eases the job of the programmer. This is how our error detector and corrector actually work, because it's a lexical analyzer. There we can have a lexical corrector. In a parser we can have a syntactic corrector. Then we get a semantic checker, which actually produces itself the correction to the things if we have the semantic errors and all. So they all give the diagnostic message printer, which prints you the exact message where the error is. It pinpoints the error, and it helps the programmer to diagnose and detect error. And there is also the simple table where we can put in many things. So then now let's talk briefly about the error recovering strategies. We have firstly the panic mode, then phrase level recovery, then error production, and global correction. The first is our in a panic mode, what we do is we discard input symbol until a synchronizing token, usually a state delimiter or a semicolon, which have a clear and unambiguous role, which is selected by the compiler designer. Unless we don't find that thing, we start discarding. The parser deletes stack entries until it finds an entry that can continue parsing given the synchronizing token on input. That is, we skip until we encounter a symbol which tells us that we should continue, right? It's very simple. What I'm actually saying is, say for example, we got a statement, some statement. Say for example, we have a statement where we say a equals to b plus c, and we forgot terminator there. And then say for example, we call d equals to e plus f, and there is a terminator. Now if we talk about the synchronizing token and we say that, hey, the synchronizing token is the semicolon, for example, that means unless I don't find a semicolon, that means end of the statement, I'm gonna skip everything. Say for example, a equals to b plus c, then I saw that there is no semicolon in it, so I found the error here. So what I do is here I switch on the panic button. So I will say the compiler will go in a panic mode, and it throws off everything until it doesn't find a synchronizing token, that is this semicolon. Okay, because up to this point we are not sure that this it's a correct thing. So but after this point we know, okay, whatever error here was, but after this there could be I can start parsing from here onwards. So whatever is after this I can start working on that. But from this point to this terminator I can't. I'm in a doubt, so I will skip this. Simple as it is. So I start parsing after this. So I will not stop here because the compiler, as we say, that it doesn't stop, it finds the errors, it doesn't stop it there, but it tries to go on. So in the panic mode, what we do is we put the panic button here until we don't see the terminator, and when we see the terminator, after that we can go on parsing, right? So we gave the message here is the terminator is missing, and this part we don't talk about anything about this, and we try to find errors after this, and we start to parse from this point onwards. We continue doing what we are doing, right? Now many compilers do it many ways. We can do it in, if you don't want to skip whole thing up to the terminator, we can do in between skipping. That's what I'm saying is, say for example we have a statement like this. We have 2 cross multiplies 3, right? That's correct, but we have double cross 3. Then we have, say for example, plus 45 minus whatever, and so on. Now when we start parsing, we said start appearances to star, and after star, when I see the double star, I know this is an error. Now a compiler knows this is an error, so it will have a panic button. But if we skip everything up to this, it's not gonna be efficient. So we can say that, hey, skip, but skip only because we know if 2 is multiplied with some integer, so this is the integer, the 3 is that integer. When we find that integer, because we were expecting, because it was like a plus a multiplies b, so if we have a which is an integer, it's multiplied with some other integer. So if after the star we were expecting the integer, so there is no need to skip up to the whole, to the term delimiter or this terminator, but to something which belongs to the grammar. So that's 2 cross 3, so we can stop it here only. Okay, we can skip only this much, right? Because we have found the integer, so we can start our parsing from the 3 onwards. So we can have our grammar like this. So we are saying that we have a grammar. We talk about the context-free grammars in a while, very shortly after this. But let me say that, for example, we have we are talking about the e, which is this expression. So we say this can be an integer, right? Or this can be a e cross e. That means we multiple. We will talk about this in detail later on, but you just have an idea here. Or this could be a simple e in appearances, or if these are the valid things, but if it's not belonging to these, that means we then have an error, right? And we say you skip. That means we're talking about how much you skip to the int, or in our previous case I could have said here a terminator, you skip to the terminator, but I don't want to skip to the whole terminator, but I want to make it more efficient. I say because I know the multiplication, it can be multiplied to another integer, so skip to that integer only, right? Right? Or you could have many more things, but here on this will skip only up to the integer, right? So this is the panic mode. It's a very simple thing. It says simply you find the error, skip unless you don't find a synchronizing key token. Well, in this case that is an integer, in this case it is the terminator, right? Okay, now next thing is the phrase level recovery. It is not only detection but the recovery in it. It performs a local correction on the input to repair the error, and also it simultaneously reports error. Okay, it not only repairs it but also reports it. For example, there was a statement a plus b, and then you thought there was a terminator, but what you've done is you have put a comma there. Now when the error is detected, it will be replaced, it will be corrected by a terminator, right? Like that. Or sometimes you say a equals to b. We are talking about if statement, if a equals to b, but what happened is you wrote like this. You wrote like this, and you forgot the double equals. Now compiler knows that this is the comparison here, and this is an error. For example, you can put up the double equals instead of single equals. Okay, or sometimes if not this a proper example, maybe I say if it was a equals to b and you said double equals, and now we know this is not a comparison, this is an assignment statement. So what you're gonna do is this is an error, so we can simply correct it by removing it, the extraneous this double equaled. Okay, or sometimes you have for I equals to 0, or you say double equal to, then maybe extra double equal to now this terminator or semicolon. Now this is an extraneous semicolon, you can remove it, or if you have missed it, you can insert it. So this is what is done in the phrase level recovery. The important thing in it is where we detect the error should be exactly where the error has occurred. If we start detecting it somewhere else, say for example the error was here and we start detecting it somewhere else, so it will be very tough to correct it then, right? And the choice of the local correction, all of these is left to the compiler designer. Now the next thing we have is the error productions. Programmer actually anticipate common errors that might be encountered, so we add our grammar with the productions for erroneous constructs. So when you are parsing and you encounter those error productions, you actually do a proper, better error diagnostic, because you exactly know now what to do, because they are pertaining to those errors, and because the production is error production was encountered during the parsing pertaining to that particular error, which we already know, so we can be in a better position to deal with that error. Say for example you have we write it, say for example a times b, for example we write it, programmer like like this, but mathematicians like this, right? AB. So we know that we may be encountering things like these in our program, so we add up a production. What is production? We will talk in detail in the grammar. So if you are not understanding this thing, wait a while and watch the videos on the context-free grammars and the productions and all. You'll understand it. Say for example we have the expression e, we can add up our expression, we have a lot of things in it, and so on, and one of the production also we have is that we can write the doubly, that means concatenated together the two e's, two expressions together without any star in it. Okay, so now this is a production for erroneous construct, right? If we have an error, now when we encounter a double e, we can have our grammar, in our grammar we can have a provision for these things, and we can do better diagnostics. We understand that actually we are missing with the with an operator in between, right? So this will help, but this will have a problem, that this is gonna complicate our grammar, because now this grammar will be augmented by these erroneous constructs as well. So these productions are also there in our grammar, so this grammar will become may become complicated and hectic. Now, global correction is something. We want to choose a minimal sequence of changes to obtain a global least cost correction. This least cost correction is a yardstick where we say how we measure our the better strategy for error correction. Now, what we do is we say, for example, we have an X as a string and a grammar G. Then this may have errors, and we have algorithms to convert this into the string Y. Okay, these algorithms which have the least cost correction algorithms, which will do what? Which will try to convert X into Y, but with the minimal changes. Okay, there will be lesser insertions, number of insertions, deletions, and the changes in the tokens, whatever, to convert from X to the Y, so that it will be minimal. Okay, but to convert X, the erroneous string X to the Y, which is supposed to have a correction, all corrections done, is really difficult, and it is only theoretical, and it doesn't come into practice because it's very tough to convert, because what we are trying to do is we are trying to see what the intentions of programmer are. So we are trying to look into the mind of the programmer and try to convert an erroneous program into the correct program. So it is really a very difficult task. So nevertheless, you have the least cost correction. It stands as a yardstick. Okay, yardstick for what? Yardstick for evaluating error recovery techniques. For example, we just saw one of the recovery techniques, phrase level recovery, for example, we saw. So we'll try to apply these algorithms to have a minimal change. Now, this error recovery can be understood practically, and we need to have some examples in it. But we have to first understand. We cannot understand it properly because we don't have a tools right now, because we need to know the context-free grammar and a lot more. Means we need to actually see the parser inside. So the next thing we will do, and maybe we come back later on to this error correction with a proper example. But first, we will deal with the context-free grammar, because the parser uses the grammar to actually parse the tokens given by the lexical analyzer, right? So let's go into the now the context-free grammar.